welcome everybody to this open lecture on higher-order metaphysics. More generally, a warm welcome from the MET program. Let me take a few minutes to say a couple of words on the program itself before introducing the open lecture itself. So, many of you might already know that it is a 2-year master, which is taught completely in English, and it is based in Lugano, Switzerland. Of course, people being here, those that are here know that we are based in Lugano, but those online maybe have not actually realized this. The requirements for admission, for being considered for admission, is of course a bachelor in philosophy, though it is also accessible as a second master in philosophy. We thought of introducing some basic ideas, let's say the essential traits of the master, by presenting them in 4 numbers. The numbers being 93% for 25 and 2000. Is 93%, are percentages numbers? Well, maybe you should not ask the marketing people. Anyway, let's start with 93%. So the math program, this master, is designed to prepare students for PhD programs. And indeed, 93% of graduates of the program who wish to pursue an academic career afterwards, which is the vast majority of the students, start a fully funded PhD after graduation. This, I think, is a pretty incredible placement record. It's hard to find clear answers when it comes to questions about placement records of other programs, but I think this is quite remarkable. In the universities where our students go afterwards include a long list such as Geneva, Oxford, St. Andrews, Syracuse, Durham, and so on and so forth. This was the first number. The second one is going to be 4. 4 are the 4 core areas of the master. So all the teaching and the program itself is focused on 4 core areas, which are metaphysics, logic, philosophy of mind, and philosophy of physics. And you see this in several aspects of the program itself, and mainly in the courses that compose the program. In this table, you find the mandatory courses of the first and the second year, including at least 1 course in each of the 4 core areas. And in the second table, you find the long list of elective courses, again, in the 4 core areas, in, let's say, crossover courses and nearby areas, and as well as our summer school. The third number is 25. 25 is the number of our professors, the professor of the program. And those 25 are leading figures in the 4 core areas of the program. And not only they are indeed leading figures in those respective areas, but they also act as personal tutors for our students. Each first-year student is assigned a personal tutor chosen among those 25. And these include Catherine Kozlicki, Kit Fine, Anna Marmodoro, Tim Maudlin, Achille Varzi, and starting next year, a mysterious new professor that will be announced in the next few months. So stay tuned for this. The 4th number is 2000. 2000 is the semester fee, 2,000 francs per semester. I think that the semester fee, at least when it comes to international standards, is pretty low. But on top of that, our students have plenty of funding opportunities in the form of scholarships and also assistantships, but also in the form of prizes. Actually, tonight, there's going to be a ceremony for the award of 3 of our prizes for the top first-year student average, the top final students average, and the best thesis of the program. So these were some basic elements concerning the program itself. In case you would like to find out more, you can have a look at our website, send us an email, or find us on social media. Right. And today we are here, indeed, for an open lecture of the master program. And as everyone actually knows, we are here for an open lecture of one of the 25 professors of the master, which is indeed Tim Williamson, who's going to give a lecture on higher order metaphysics, an introduction to higher order metaphysics. I guess many of us are here in order to know something about higher order metaphysics without having to read something about higher order metaphysics. And hopefully, Tim will indeed explain to us what this is. Okay, Tim, please.
Okay, good. So I'm going to be talking about what's arguably the most significant new development in general metaphysics over the last 10 or 12 years. And that is higher order metaphysics. So I'll explain something about what it is and what its advantages are. But I mean, very schematically, higher order metaphysics is metaphysics done within the framework of a higher order logic, and I'll say what that is as well as I go on. But the particular sorts of aspects of metaphysics that higher order metaphysics makes a difference to are ones involving, as one would usually say, things like properties, relations, states of affairs, propositions, and as it were, things like that. And the advantage of this higher order framework is that it enables us to get more precise and rigorous about these matters, but also that in certain key ways it actually simplifies how they can be treated. I mean, that it might seem like this is going to be something very abstruse and difficult, but in fact, in the end, if doing things a higher order way, actually it wipes out a lot of unnecessary complications, which have sent a lot of discussion of these matters on the wrong track. And the advantages of it are to do with quite subtle issues that depend on just what language you're working in and how it's structured from a logical perspective. And it might seem odd that these apparently rather abstruse linguistic distinctions make a serious difference to metaphysical theorizing. But this is actually an example of a much more general feature of philosophy, which was very well summed up by Bertrand Russell. He wrote, a good notation has a subtlety and suggestiveness, which at times make it seem almost like a live teacher. So that just working in the right sort of language can send you in the right direction, and more strikingly, that working in the wrong sort of language can send you off in very bad directions. And so we'll see in practice how that works out in the particular case that I'm going to be talking about. So higher order logic that's contrasted with first order logic. So we need to say something about what the difference is. So the characteristic feature of first order logic is that, roughly speaking, the only kind of generalization you can do is generalizing into name position from a grammatical point of view. So for example, when you make an inference from Alice laughs to someone laughs. That's an inference by generalization, existential generalization. You're generalizing into name position. What you've done is you've replaced the name Alice by the quantifier phrase someone. I mean, actually, it's not strictly speaking confined to names, but there are things which grammatically occupy name position, like demonstratives, this or I or whatever could also count. So second order logic, it extends first order logic by also letting us generalize into predicate position. So we can go from Alice laughs, the same premise, to, well, I put it in English as Alice somethings, which of course that's not really grammatical English, but it's the best way of getting us a flavor of what's going on in second. This is just second order quantification. It's quantifying into the place of an ordinary predicate. And if you formalize these things as is done on the handout, you get a variable which is occupying predicate position rather than name position. And if you just think about it in crude philosophical terms, you might describe what's going on as generalizing over properties, so that, as it were, you might think, well, this is really what we're doing is going from Alice has the property of laughing to someone has Alice has some property. That's actually a very misleading way of putting what's going on, but it sort of gives you an initial flavor for what's happening here. So that, as it were, it's simply, if you like, generalizing this capacity to generalize from, putting it another way, from subject position to predicate position. And it seems like, particularly for philosophical purposes, where we are interested in being general, the more capacity for generalization we have, the better. So that is just, so far, is what would be called second order logic or second order quantification. But when we're talking about higher order logic, we're not just thinking about the second order, but about taking this process of generalization even further. And so, for example, once you've got someone laughs, you could think of the someone there as a kind of predicate of predicates, because in a way what the someone is doing is it corresponds to the predicate of being instantiated, which you're applying to laughs when you say that someone laughs. And so in a higher order logic, more generally, you can generalize into any grammatical position at all. There are a few little I's that need to be dotted and T's crossed there, but it's that is basically what the situation is. So that every constituent of the sentence has a position that allows you to generalize and to say something which would be entailed by the original sentence, but also be entailed by other sentences with as something else occupying that same grammatical position that we were generalizing into. So that as it were, higher order logic is a type of logic where you can generalize into any position that you like. And in particular, it's not just one place predicates like loves, but also two place predicates like loves and hates, and in fact many three place predicates like between X, or X is between Y and Z, and so on. And it also allows you to generalize into sentence position. And in fact, people often think of sentence position as just a special case of predicate position where it's a zero place predicate. In other words, it's something that you don't need to add any names to get a full sentence. Whereas, just as an instance of the general principle that if you've got an n-place predicate, what it requires in order to make a full sentence is n names to plug into the gaps. And with a sentence, you don't have any of those gaps. And so if it's more than one place predicate, then we'd informally think of that as talking about generalizing over relations. And with a zero place predicate, where in other words, a sentence, what we're generalizing over seems to be something like propositions or states of affairs, something of that kind. And that certainly is useful, for example, when we want to make explicit the generality of some kind of logical principle. So, for example, with the law of excluded middle, you can formalize that in higher order logic as what I put on the handout for all P or not P. So the P there it's occupying the position of a sentence, right? It's not a name of a proposition. It's just a sentence, and that could be quite useful for logical purposes if you can formalize a principle as a universal generalization, because one thing that it allows you to do if you want to is to negate the principle. So that, for example, in intuitionistic logic, the law of excluded middle isn't valid according to that logic. And you might want, if you might want to express your rejection of excluded middle by denying it. But if you're just working in a kind of standard language where you just have instances of excluded middle, like things like either it's raining or it's not raining or something like that. In this particular case of intuitionistic logic, it happens that actually, if you try to deny any particular instance of excluded middle, you end up contradicting yourself, even in intuitionistic logic. And so you can't consistently deny any particular instance of it, but you can consistently deny the universal generalization. I don't want to go into the details of intuitionistic logic, but that's basically because intuitionistic logic kind of goes non-classical and non-standard when you get to infinite totalities, and so what's allowing them to deny the general principle is because it has infinitely many instances which you can't represent them all together in the language. So one thing that you can do with quantifying into sentence position is to make generalizations explicit, so that you can you can deny them, or you can make them be the antecedent of a conditional. You might say, if the law of excluded middle holds, then blah, blah, blah. And then you can replace the law of excluded middle holds by the actual formalization of the law of excluded middle. One thing to emphasize about the kind of generalization that we're doing here is that we're not just lumping together all instances of the law of excluded middle, or whatever kind of generalization we're concerned with. I mean, you might think that for all P or not P is really just equivalent to asserting P or not P, where the P gets substituted by any sentence in the language, so that we're just asserting as well excluded middle for all the sentences of the language. But that's not the right way to understand what's going on. And it's for the same reason that just in ordinary first order logic, you can't understand a universal generalization or as just asserting each instance of the principle in the language itself. And the reason for that is that in order to get an instance, you need to have a name of the relevant object. And so for example, if you wanted to have a generalization like everything changes, for example, you wouldn't have captured the full meaning of that if you just said, Lugano changes and Oxford changes and I change, and if you just went through a list of all the things that you could name or pick out with a singular term in the language, because that would still leave open the possibility that there was something that you didn't have any way in the language of referring to that didn't change, and so that it might be a counterexample to the principle, even if all the things that you could name were not counterexamples. And so with first order generalizations, just generalizations over objects, it's important to understand that they're not simply over the objects that you can pick out in a particular language. They're just over all objects whatsoever. And the same kind of spirit applies to higher order generalizations, as we might say, over all propositions or over all properties or all relations, because what we're trying to capture is something more general than just, whatever happens, whatever holds of those propositions or properties or relations that we can actually articulate in the particular language we're working in. We don't want to be restricted to them. We don't want what we say just to be true merely because our language isn't capable of specifying a counterexample. We want to allow that there are, as it were, counterexamples out there, whether we can actually articulate them in the language itself. And so the quick way of saying that is that these generalizations are not to be interpreted substitutionally. So let's, I've mostly been talking rather abstract, but let's talk about a particular kind of case. So one example is higher order logic gives us a characterization of identity, and it's basically that the two principles that are relevant here are that what's called the indiscernibility of identicals and the identity of indiscernibles, both of them associated with Leibniz. And so we can capture that in higher order logic by saying that, well, this is the formula I've got on the handout, that for all x and y, x is identical to y if and only if, and we could read it something like everything that holds of x holds of y and vice versa. And so the principle, this principle, I'm going from left to right, it's saying that if x and y are identical, then everything that holds of x holds of y and vice versa. That's what's not usually known as Leibniz's law. And then the converse, going from right to left, is that if whatever holds of x holds of y and vice versa, then x just is y. So that's a kind of explicit, necessary, and sufficient condition for identity in terms of the second order quantification into predicate position. And from that, we can easily derive standard consequences. For example, you can infer from A equals B and F of A to F of B. And so just to give an example, I wanted an example with two names that refer to the same object, just to make it non-trivial and the identity true. And so if you're curious, Derry and Londonderry are two names of the same city in Northern Ireland. It's just if you're a Roman Catholic, you'll call it Derry, and if you're a Protestant, you'll call it Londonderry for historical reasons that we can go into. And so you can, so from the identity, Derry is Londonderry. An identity that people on both sides of actually the divide are going to be a bit reluctant to assert, because for each side it involves saying the name that they don't like. But and then Derry is on the River Foyle. You can go to Londonderry is on the River Foyle, and that's just, you're just plugging in the predicate is on the River Foyle for Z. So that's just an example of how you can use quantification into predicate position to capture a standard principle, and it seems reasonable actually to describe this principle as both a law of logic and a law of metaphysics. I mean, it's a law of logic, given that it's correct, because it's stated in purely logical terms, and of course it's true. So it's perfectly general, except for we've got a specific predicate identity in there, but that's by most standards a logical notion. But it also seems to be a principle of metaphysics of a very, very general kind, because it's telling us what what's necessary and sufficient for things to be identical. It's not talking about language. It's in language, but it's not about language. And it's just telling us something very general about identity. And that seems like a pretty metaphysical kind of thing to be giving us information about. So that's just a very quick initial sketch of how the higher order language works. If anybody has got questions of comprehension, by the way, you're welcome to ask them in the lecture. I mean, substantive objections, we probably better leave until the question period. But okay, it doesn't seem that anybody's got anything very urgent. So I think you might feel something like this. Okay, well that all seems fine and maybe quite nice, but what's the big deal about it? And in particular, why do we really have to do this with all this fancy generalizing into predicate position? Couldn't we actually say all the stuff that we're really interested in just in first order terms, which is kind of how we would articulate these higher order generalizations in a natural language such as English. Because you know it would seem quite natural to articulate the principle of identity as something like things are identical if and only if they have the same properties. And maybe the law of excluded middle as a generalization, couldn't you articulate that by saying something like every state of affairs either obtains or fails to obtain. And so I think, well, if we're putting things that way, we could just use this ordinary first order quantification, but quantify over special entities like propositions or states of affairs and properties and relations. And, because after all, if you take words like proposition or relation or property, they just seem grammatically, they're just like ordinary nouns like stick or stone or cat or dog. And so it seems that what's going on, does it really require all this kind of fancy grammatical stuff about generalizing into predicate position? Because can't we just do it in the very same, using the very same kind of apparatus from a grammatical point of view that we use in making generalizations about cats and dogs, except I mean we'd be talking about some abstract objects in some sense like properties and relations, but it doesn't really seem, if you just think of it so far, that we've made a huge amount of progress, that it seems that we could be doing what's being described, for higher order logic, but just using first order logic as far as the grammar went, but making the generalizations be about these special entities. So the heart of the matter is why that tempting thought is wrong, why you cannot do the same stuff in first order logic by treating things like properties and propositions just as more objects, or simply of a more abstract kind, and then just using ordinary first order quantification into name position to talk about them. So I think to kind of tease out what the difference is, it's useful to, just as an example, to think about the case of identity again. And so it seems like this is now at the top of the second page of the handout. Couldn't we get the principle about identity in first order terms by just putting what I've written there, that for all x and y, x is identical to y, if and only if for all z, x has z, if and only if y has z. So z here, I mean, the relevant values of z will just be the properties, because we're talking about having a property. And so, if you look at the comparison between that principle and the previous principle for identity on the first page of the handout, there's not very much difference between them. The difference is just that in the second order principle, you've got a capital Z or Z to indicate that it's occupying predicate position, whereas in the first order case, the Z, which we're interested in the instances of it where it's a property, but where the value of the variable Z is a property. But we've also got X H Z, which means X has Z. And the reason why we have to bring that H in is because if we got rid of it, we would just have X Z, where we were writing two things in name position, one after the other. And as Plato already pointed out, you can't get a sentence just by stringing a whole lot of names together. You've got to have something like a predicate as well. Because if you just say John, Mary, that doesn't, as it were, say that anything is the case. You've got to have some kind of predicate to link the names. I mean, you could have a language where you didn't actually make it explicit, but it would still have to be understood in order for to get something that could occupy sentence position and that could be, and which you need because remember you've got X H Z if and only if Y H Z. So the things flanking the if and only if need to be sentences. So what you've got is you've kind of squashed all the variables into just first order variables, but in the price that we paid for doing that is that we've introduced this having relation between an object and the properties that it has. Now again, so far this may seem like incredibly small difference. I mean, you can see that it's going to have some knock-on effects because there's something is going to be a little bit complicated in the logic, because supposing we just think how can we get from this principle that if we start from the premise Derry is Londonderry, which that's be an identity, we can get the inference from that and Derry is on the River Foyle to Londonderry is on the River Foyle. So what I mean, and that's kind of the sort of thing that we want to be getting out of this principle, and just inferences like that. So with this kind of first order principle for identity, we can infer from Derry is Londonderry, we can infer Londonderry has every property that Derry has. But we still have to get from that, and Derry is on the River Foyle, to Londonderry is on the River Foyle. And there's a bit of a gap there because, if you just have Derry is on the River Foyle, and then you have this principle about the two things having the same properties, we haven't quite got how the properties hook up to the other stuff in the sentences. So the properties are coming in out of the blue, and so the way to think about it is, if we've got that Londonderry has every property that Derry has, and we have Derry has the property being on the River Foyle, then obviously it follows that Londonderry has the property of being on the River Foyle. And so we've still got a little bit of a gap there, which has to do with how the word property is getting in on the act, and then how we can eliminate it again. So, so what we need to do is we need to go from Derry is on the River Foyle to Derry has the property of being on the River Foyle. And then from Londonderry has the property of being on the River Foyle, which is what we would conclude from that. We'd get via the principle of identity, we'd get to Londonderry is on the River Foyle. So we've got to be able to, as we're cash in and out, the property thing. And that's something that's kind of forced on us by working in these first order terms, where we're talking about properties and having properties. And so that, at first, that seems okay, because surely we've got something like the principle that something has the property of phi-ing, if and only if it phi's. And you can just plug in any predicate for the phi there. And so that's the principle I've called first order comprehension. Actually, strictly speaking, the comprehension principle is something slightly different, but so this is a slightly misleading term for it. But I mean, this is the way that it hooks it up, most straightforwardly to the argument that I'm talking about. So basically, what I'm calling the first order comprehension schema, it's telling us that all this talk of property, of having properties of phi, it can just be cashed out in terms of the predicate itself, and so that it's kind of just there for the logical apparatus, but it's not really providing any kind of block to the inferences that we want to make. And so the first order approach will work quite smoothly and in a way very similar to the higher order approach if you have the first order comprehension schema that I've given you. But the kicker is that the first order comprehension schema is logically inconsistent. So that's a bit of a problem for the first order approach. I mean, it'll work smoothly if you've got this principle, but this principle is inconsistent. And so let me explain how the inconsistency arises. And if you know about Russell's paradox in set theory, you'll see that what's going on is very, very similar to Russell's paradox. And in a way, the first form that Russell even raised his paradox in was actually something a bit more like this paradox. It wasn't exactly in terms of sets. So I'll explain how this inconsistency arises. So the first thing is we're going to be concerned with a funny property, the property of not having yourself. And just to make clear how that's arising. So we could start off with, let's say something has the property of being a cat. And then the comprehension principle tells us that something has the property of being a cat, if and only if it is a cat. So it's basically saying all this kind of fancy talk of having the property of being a cat can just be eliminated. Don't worry about it. It's not adding anything or subtracting anything. And so, so one instance of that is that if you take the property of being a cat, that is not itself a cat. I mean, it's an abstract object, presumably, unlike cats. And therefore, the property, since it's not a cat, the property of being a cat does not have itself. Okay. Whereas if you take the property of being a property, then the comprehension principle is telling us that something has the property of being a property, if and only if it is a property. That's really just plugging in, it is a property for phi. And of course, the property of being a property is itself a property, right? Obviously. And so it has the property of being a property. And in other words, the property of being a property does have itself. Right? And so it seems like you can just classify properties into the ones that have themselves and the ones that don't. I mean, normally we would, I mean, with regular properties, I mean, they just kind of everyday ones, they're not going to have themselves because, you know, there are things like, you know, being happy, and the property being happy is not itself happy, and etc. So now what we can do is we can formulate the property of not having a self, and that just corresponds to the formula not XHX in the first order language. It says it's not the case that X has X. And so this is, on the first order approach, this is just, you know, one more property. Even. And then if we plug this property into the first order comprehension schema, what we get is that for any X, X has the property of not having itself, only if and only if X does not have X. So that's just plugging in, you know, not, it's not the case that X has X for phi in the comprehension schema. So now let's take the particular case where X is the property of not having itself. And I mean, what you get is quite a mouthful, but it's because we've got that on if you're looking on the handout, we've got this principle for any X blah blah blah, X has a property, and then we've got a particular value of X, the property of not having itself, which we're plugging in, and what we get is the property of not having itself has the property of not having itself, if and only if the property of not having itself does not have the property of not having itself. And I mean, that's obviously quite hard to get your mind around, but the thing to notice about it is that it's of the form P if and only if not P. The P is this complicated thing about the property of not having itself has the property of not having itself. But the overall structure of that thing that we've got is of the form P if and only if not P. And P if and only if not P is, it entails a contradiction in classical logic. That, I mean, you know, you can derive from it, you can derive P and not P. And so, at least within classical logic, this first order schema is actually inconsistent. So the thing that we needed in order for the first order approach to thinking about, for example, identity in terms of having the same properties, the principle that we needed to make all of that work is an inconsistent principle. I've said it, P if and only if not P, that it's a contradiction in classical logic. I mean, of course, if you're sympathetic to non-classical logics, you might start thinking, well, but couldn't we go non-classical, because aren't the non-classical logics where you can have P if and only if not P without everything collapsing. I mean, what I would say about that is, well, two. I mean, one is if you start giving up classical logic or having something weaker instead, that has repercussions all over your theorizing. It may well have bad consequences for just standard mathematics, and just weakening your theory in that way is a very bad move. I mean, of course, you know, much more needs to be said about this, but I would strongly discourage that reaction. But also, giving up the classical logic, it would only be justified if really there was no classical way of handling this situation where you don't have to give up classical logic. And in fact, it will turn out that there is. So what are people who are sympathetic to the comprehension principle? What are they going to do here? Well, it seems that what we might expect is that they will say, well, we have to weaken the comprehension principle. We've got to make some restriction on it, and we've somehow got to rule out these funny instances with funny alleged properties of things like not having yourself. So you can try to go that way. It's very hard to find any really nicely principled ways of restricting this comprehension schema without making it so weak that it can't really do the work properly, and you can't get what you want to get out of, for example, the principle about identity. I mean, if you know something about the case of Russell's paradox in set theory, you might think, well, what about the things that have worked in set theory? Because if you're doing set theory as part of mathematics, you also have to block a completely analogous paradox. I mean, the paradox just has to do with sets that are not members of themselves, and then the set of all things that are not members of themselves. And so it's true that, you know, in standard set theory, the ways have been found of blocking the paradox. But the kind of restrictions that are involved are ones that are much less plausible for properties than they are for sets. So just to give you an example, in standard set theory, the restrictions that have been introduced to block the paradox are ones which have the consequence that no set has a complement set. So a complement set of, you know, if you start with a set X, then the complement set would be the set of all and only things that are not in X, right? And it turns out in standard set theory, no set whatsoever has a complement. And that seems like it might be okay for sets if you think of sets as somehow being built up from their members, and then, you know, you might think, well, there won't be a way of building up the complement of a set from its members. But if you think in terms of properties, we surely want that for any property, there is also the property of not having that property. You know, if there's a property of standing, there's also a property of not standing. And if there's a property of being happy, there's also a property of not being happy. And so it would be very, very drastic indeed if you just tried to copy what people have done in set theory, but for properties instead. So, I mean, it's not that you couldn't come up with anything. It's just that what you'd come up with in restricting the first order schema to avoid the paradox, it would be a loss in both simplicity and in strength. It would give you a much weaker principle that made it harder to squeeze out the kind of ordinary consequences that I was talking about. But it would also be, you know, a more complicated theory. And you know, one sign that this is something is going wrong here is that if restrictions are needed, you'd think that you'd need them in mathematics, where you use principles like this about identity all the time. And you'd think that you needed some special kind of care when you were applying the principle of identity. I mean, that you wouldn't be able to always to prove that if you got X phi's but Y does not phi, therefore X, you couldn't always conclude that X and Y are distinct, because what if the property of phi is one of these funny properties that for which the comprehension principle doesn't work? And but in ordinary mathematics, it doesn't seem that you're doing any kind of monitoring to check that the properties that you're using in the in reasoning about identity are not funny properties. You're just kind of going ahead and using them. So it seems like if you try to do all of this in first order logic, you get into a mess. And of course, it might be that that's just a mess that we have to be prepared to live with. But the thing is that none of this mess occurs in higher order logic. You cannot formulate any analogous principle that will lead to a paradox in just see in higher order logic, because there's nothing like the having relation, and we're just what we've got. If you look, we've just got a predicate variable and a first order name variable as well, and so we can't make those be the same variable, because they're simply of quite different grammatical types. And so the kind of collapse that happens with the first order principle just doesn't happen, and can be, you can show that it doesn't happen in higher order logic. And in fact, you could even show using just first order logic that you don't get this collapse in higher order logic, because you can prove its consistency just by using first order means. And so you can have a completely unrestricted principle, for example, of identity, like the one that I put on the first page of the handout, and you can have everything that you need to just to be able to plug in any predicate you like into principles about identity or principles about anything else in higher order logic without any paradox at all. And so it's both that you don't have the paradox, but also that you haven't had to pay some kind of price for avoiding the paradox by some kind of messy restriction, so that you're dealing with a principle that, as it were, when maybe most predicates are allowed to instantiate it, but some are not. And so thinking about things in this way, it avoids a paradox, not by some kind of ad hoc means, but just because it doesn't get anywhere near the paradox in the first place without any need for restrictions. And I think it's both a sign that we're on the right lines, that we're not getting a paradox, and it was a sign that we were on the wrong lines with the first order approach, because we were getting a paradox. And it's also going to to mean that the logic will just go more smoothly. And I think this has all sorts of advantages from the point of view of metaphysics as well. So, for example, you know, we're not having to do all this business about you know, the having relation, and then you can worry, well, you know, about maybe if we've got a having relation, then do we get some kind of regress because if X has Y, then, you know, if X has the relation of having to Y, then won't be a further relation which holds between X and having and Y, and, you know, and sort of some kind of multiplication of relations like that. So none of that makes any sense on the higher order approach. Those questions don't arise, and it's not so much because we banned them, it's just because the way the language is structured, there's no temptation. I mean, there's just nothing in it that lends itself to those kind of issues. And I think we also avoid a whole lot of rather kind of pointless disputes that you can get into in the case of first order property theory, like, you know, where are properties located? Do properties have parts? Are properties parts of the things that have them? And issues like that, which have led to endless, pretty sterile debates in metaphysics. And I mean, you can effectively just not go there because there is no such place to go, but by adopting the higher order framework. And so I think it's something that enables us, arguably, to avoid a lot of a kind of time-wasting disputes that can otherwise arise in metaphysics. I think another reason for preferring this higher order approach is that it's actually consonant with quite a lot of what goes on in mathematics. So it's where this isn't just something that philosophers have cooked up. The kind of quantification that I've been talking about, second order quantification, it's actually needed in parts of mathematics in order to capture the intended meaning of various mathematical principles. So I mean, some of those are axioms of set theory, things like, if you come across them, if you haven't, it doesn't matter, but the axiom of separation and the axiom of replacement. But one that you may well have come across is the principle of mathematical induction. I mean, what that tells you is, putting it in terms of, you know, the loose way of talking, putting it in terms of properties. So this is a principle about how you can show that all natural numbers have a certain property. So the natural numbers are 0, 1, 2, 3, 4, 5, and so on, you know, just adding one as many times as you like to. And so the way that you standardly prove that all natural numbers have a certain property is that you prove that 0 has the property, and then you prove that if any number n has the property, then n plus 1 also has the property. And once you've done those two things, mathematical induction allows you to conclude that all natural numbers have the property. And, you know, as I've said, the principle involves some kind of generalization over properties. And when you use it in mathematics, you're not interested in, is this a proper property or something like that? I mean, it's just any old property that you come up with in mathematics. If you can prove these things about it, you can apply mathematical induction. And so there's a natural mathematical need for this kind of generality. And and one way that it comes up is that if you try to just replace this kind of generalization over properties, so-called, I mean, but actually it's just a higher order generalization in mathematics. If you just try to replace it by some kind of first order principle where you don't go higher order, it turns out that however you do that, if you're working in first order logic, there will always be models of what you're saying that are non-standard, in the sense that you'll get that in the model that there'll be some natural numbers beyond all the ones that you can get by adding one as many times as you like to zero. So that there'll be, as it were, you'll have all the the standard natural numbers. And then in these non-standard models, you get a whole lot more natural numbers on at the end of these. After this goes all the way up to all the proper natural numbers, and then you'll get some non-standard ones at that case. If you just try to do work in first order terms, you'll not be able to exclude these extra things, which are intuitively, these are not natural numbers. The natural numbers are just the things here, but you can't actually articulate a principle that will ban these extra things if you just work in first order terms, but you can articulate such a principle in second order terms. So that there's actually some kind of encouragement from mathematics for thinking in these second order and higher order terms, because that actually is what you need in order to provide a setting where you can properly capture what mathematicians are getting at when they talk about, for example, the natural numbers. And more generally, something I haven't been putting so much emphasis on, but quite a lot of the discussion in metaphysics about properties is, well, what's a real property and what isn't? And, people are a bit reluctant to have disjunctive properties, like the property of being, either green or square or something like that. People think that's not a proper property. But of course, once you have all those restrictions on what you count as a proper property, then the effect is that generalizing over properties doesn't actually have the logical power that it needs to have, because you can't just plug in any old predicate for this generalization about properties, because the predicate might not pick out a proper property. Whereas the approach that you get from higher order logic, which is completely consonant with the way that properties, as it were, are talked about in mathematics, is one where just any old predicate, provided that it's sort of grammatical and so on, will give you a property. And so, I mean, of course, you can say that there's some kind of elite of perfectly natural properties or something like that. That's a different matter. But when we're just, for logical purposes, generalizing over properties, so there shouldn't be any of these kind of restrictions that you get if you start thinking properties ought to be something natural or whatever. And you get those restrictions if you work in first order terms, because well, you'll get the paradox. And so I think that from the standpoint of higher order logic, just insisting on working in first order terms, it looks a bit like Procrustes' bed. I mean, maybe you know this story from Greek mythology that there was this guy Procrustes who had a bed, and and he if you made the mistake of visiting him, he would insist that you would sleep on this bed, and anybody who was too short for the bed would be stretched until they were long enough to fit the bed, and anybody who was too long for the bed would have bits chopped off them until they were short enough for the bed. And so from a higher order point of view, the first order logic, if there's an insistence that everything has to be done in first order logic, I mean, it's not wrong in itself, it's just that the first orderism, as it were, the kind of dogmatic restriction to first order logic, it looks a bit like Procrustes and his bed. So if you don't want to be stretched on the rack and you don't want to have your feet chopped off, then I suggest that you go with higher order logic. Thanks. So yeah. So I think we've got time for, for questions.
Thank you. So usually quantification, or as it's called nowadays, are directly related to existential claims. And so I was wondering in these, so when you're quantifying, when you're using that there exists, are you meaning is that an existential thing? And if so, if you're allowing all these properties, you will have to not have you will have to have something like the property of not equal to itself. There is no such thing as a property of not equal to itself.
Well, so yeah, just on the last thing that you said. So in higher order logic, there's no problem about having properties. I mean, just crudely talking about them like that for convenience, but having properties that nothing has. And in fact, for any property, there's the property of not having it. And so since there's a property of being self-identical, there's a property of not being self-identical. And that doesn't lead to any contradictions. Just basically, in that respect, it's like set theory. I mean, in set theory, you have the empty set, and the empty set does not create any problems whatsoever in set theory. But yeah, in terms of the question, so you were asking whether this is an existential quantifier. So this is the thing that I was kind of joking in, sort of reading in pseudo English as Alice somethings. By contrast with, there exists X such that X not. So it sort of depends what you mean by existential. These two things, what you can't do is to think of them as both restrictions of some more general notion of existence, that so the meaning of this is, in a way, is kind of incommensurable with the meaning of this. And so if we're thinking of the existential quantifier as something individuated by its semantics, the semantics will be different, because we will have to actually to give the intended semantics for the second order quantifier. We would need to do that using second order quantification in the meta language to capture the right idea. And I mean, I think what you can say is that these are, to some extent, analogous terms. I mean, by the way, there's a kind of an issue in first order, sorry, in higher order logic about whether you think the backward E really is really the same backward E in both these cases, or whether it's just a kind of symbol that kind of takes its meaning depending on what type of variable we combine it with. But if you look at the whole quantifier, these do not mean the same thing, and so, as I say, if you individuate them semantically, they're not this. And if you say that an existential quantifier has the meaning of this, then this one is not an existential quantifier. But it's true that a lot of the logical principles will have the same structure. I mean, for example, when we're doing, existential generalization, from an instance to the generalization, that will have the same general kind of logical form as in both cases. And when we're doing a universal instantiation, that will also be a kind of very similar move in both cases. But it's really just a matter of analogy, right? It's not that we've got some single thing that that we can then kind of restrict in various different ways at the level of the semantics to get these different notions. It's that we just have to live with the idea that there are all sorts of features that occur at different points in the in this hierarchy of grammatical types in the language that are kind of structurally similar to each other, but not exactly the same. So I think the best thing to say is it's not strictly speaking existential in the semantic sense, but it's kind of does function in roughly the same way.
There seems to be some way to express comprehension, something like a comprehension principle also at the second order. Like, for example, we want to say that there is a property that's this way, corresponding to any condition satisfied by some object. So the formula would be for all phi, there is an x, big X, such that x of x equal to phi. Doesn't this get us into troubles again?
No, it doesn't. So you can have things. You do have onerous comprehension schemes for second order logic as well, and they look. So yes, just to write on the board what you were saying, it'll say something like there exists x such that, let's say, for all y, so y if and only if phi of y. So phi of y could just be any old predicate. Yeah. So that's valid. That's a valid schema in second order or higher order logic. And it is saying something that you could crudely read as there is a property which such that the things that have it are all and only the things that phi or something like that. And so you might think that you can somehow get a version of the paradox from this, but you can't because there's nothing that corresponds to the crucial instance. It's not the case that x has x, and that's because there's also nothing that has the form of x has x, because because we're dealing with two variables here of different types. Big X here is in predicate position, little y is in name position, and And so you can't have something occupying both positions. And so you will, if you just fiddle around, you'll see that you just can't get anything like this. And in fact, I mean, you can prove that this schema is consistent because you can build models for it within set theory. I mean, because it's in set theory, the models are not exactly capturing the intended meanings of these expressions, but they're enough to show that that this is not going to collapse into a contradiction. And if you want to get a kind of feel for what's going on, again, it's not exactly accurate, but it kind of gives a sense of what's happening. The problem in the first order case is that you're trying to kind of map all properties to individuals, and if you think of a property just for these purposes, you can just think of it extensionally, a property as being just like a set. You know, what you're trying to do is to map all subsets of the set of individuals to particular individuals, and and not map different subsets to the same individual. And so of course, Cantor's theorem tells you that is impossible because there are always more subsets of a set than there are members of it. And so that's just in a kind of combinatorial way. That's really kind of what's going wrong with this first order approach, because it's insisting that everything, as it were, can be represented within the first order domain, and so it's trying to map, if you like, subsets of the domain into members of the domain, and then that it's going wrong for combinatorial reasons. Whereas with the second order approach, you're not in any way identifying the as it were the property, i.e. what's going on in the second order with any particular individual. I mean, you can see that just isn't, there isn't any individual being picked out here, and it's because you're not trying to squeeze everything in, as it were, into the bottom level of the hierarchy, that things stay consistent, and they stay consistent really without well, you don't have to lift a finger to make them consistent. It's just following through the spirit of the approach just automatically preserves consistency, and so it's this kind of, as it were, reductionist aspect of the first order approach, that everything has to be reduced to the first order. That's what's producing the inconsistency.
Point about before you have said that in higher-order metaphysics we don't have to be worried about the properties and parts or something like that.
Yeah.
And I don't understand why.
Oh, okay, because when you talk about things having parts, you're talking about a kind of, as it were, something like X is a part of Y. And then, so X and Y these will both be sort of occupying name position. I mean, that you could just name put in names of the objects that you're interested in there. But if you go to second order logic, you'd need to put in a second order variable in one of those places in order to raise the question. But that doesn't make any sense. I mean, because if you put a predicate So for example, you put X as a part, let's take the predicate is happy. Oh, well, let's just the part of laughs. Let's say laughs. X is a part of laughs. That's just, ungrammatical. It doesn't, because the syntactic types they don't fit together properly. And so trying to raise the question would just give you total nonsense. And if you try to do it at the other end as well, you get you get equally nonsense. You get laughs is a part of Y. And so these kind of issues which you can sort of raise grammatically in an approach which is treating postulating properties as objects that you could talk about in the same way as you can talk about other objects. It enables you to ask these questions, but if you just insist on the kind of type distinctions between names and predicates, there just is no question to ask there, and I think we're better off not having such a question. So I think these kind of questions about as I say, whether properties can be parts of objects or whether they have parts, they're just a kind of artifact of a sort of approach to the grammar of metaphysics that just isn't well motivated. Yeah, go on. You're not looking satisfied. Yes.
Then I think that X and Y have that property. They are property of properties.
Well, yeah. So if we have X as a part of Y, so and we'll think of is a part of as here as a kind of two-place predicate. Then you definitely in second-order logic you can go from that to for some R, X, R, Y, where R is a variable that occupies two-place predicate position. So that move is absolutely fine, but it doesn't raise any kind of special metaphysical problems or anything like. And you could. I mean, you could then. Yeah. So.
But now we are speaking about parts of properties.
We're not. So we're not speaking about parts of properties. So little x and little y. This could be, let's say, x could be Lugano, and y could be Switzerland. And then what we get is that there is an R such that Lugano are Switzerland. But it's not, that's not saying anything about parts particularly. It's just saying that, if you like, that Lugano is, that there's some way in which Lugano is related to Switzerland. So it's kind of, it's really not giving us anything more than we had to begin with, and it's because of the grammar of is a part of, that you're not going to get into any of these kind of strange metaphysical questions about the mereology of parts or whatever, because if you tried putting X as a part of, well, actually that was pretty much what we were concerned with over here. It's just, once you remember that X occupies predicate position, you see that this is all just ill-formed, and it's just just the grammar isn't allowing it, and there's no reason why the grammar should allow it, because that isn't how the language is built up.
Thank you very much. It was a great introduction, advertisement for higher-order logic. So you told us a lot of beautiful things about higher-order logic, but what about some problems that it has? And this is one. So one question, very open question, perhaps. What do you think are the main problems of higher-order metaphysics and metaphysics done using higher-order logic? You have told us only good things. But
Yeah.
what about that?
Okay.
Sorry, just
yeah.
There's a little point about the last issue that was raised. So you said that not only that, talk of partial or mereology of properties doesn't make any sense in this framework, but also that location talk doesn't make any sense. And that seems, I mean, maybe you're right, I don't know, but my impression is that the case there is slightly different, because you may have, for example, adverbs of place that say things like here she's laughing, or here, and there is something that some things, and the here seems to add something, doesn't make it automatically ungrammatical.
Yeah.
And I'm not sure how here is to be treated in this case.
Yeah.
But one possibility is that it's sort of like a property of a property, or
Yes.
somehow can be treated as making sense.
Yeah.
Okay.
Well, so if you take here as something that can be just, you can add it to a sentence and build a more complex sentence from it, then it's playing a different role from what it plays when it's simply a singular term referring to the place where we are. And I would suggest that, in fact, the relation between them is that we've built, what we've really done is we built we built a different operator, because we've got the at thing, and there we can put combine that with any name of a place, and then we've got at, so we've got sort of at here, except that we just shorten that to here, and so I think the action is with the at. If you want to know what something that people who don't like higher order logic will emphasize it, and which they will present as a big advantage for first order logic over higher order logic. First order logic is it has a semantics for which, and a proof theory for which, where it's such that it's sound and complete. So that, in other words, we've got a kind of notion of validity in terms of the models of first order logic, and then and validity is preserving truth in all models, and we've got a proof theory for first order logic where we can prove all and only the things that are valid on the semantics. So we've got a soundness and completeness here. For higher order logic, on the kind of interpretation that I've been giving of it, where there are just no restrictions on what properties you have, you can show that it is not complete. I mean that there just cannot be a formal proof theory for it, and such that the things that all and only the arguments that are valid on the intended semantics are provable. So that definitely means that first order logic is, in some ways, it's more tractable, because we can finding out whether things hold in first order logic. On the whole, it's not too difficult. I mean, it's not decidable, but we've got much more control over that. But I think the strength, I mean, the advantage of first order logic in terms of soundness and completeness is just the obverse of its disadvantages, and in particular, its expressive weakness. So for example, one thing that you can prove is that you can't express the idea of there are infinitely many Fs in first order logic, and the reason for that is that I can go into more detail, but when you're talking about infinity, you're talking about things which are, you're talking about, I mean, the logic of infinity is basically non-compact. And what that means is that you can have a set of sentences where every finite subset of it is consistent, but the whole set itself is inconsistent. And the reason you can have that is because, I mean, take an example like there are not infinitely many. Well, I think there are, let's just say there are only finitely many planets. But you could say there is at least one planet there are at least two planets, and I mean, so, well, three, and then through all the natural numbers. So we've got, this is an infinite set of sentences, and in terms of the intended meaning of these sentences, this complete set is inconsistent, because if all of these ones are true, then there are infinitely many planets, and so you cannot have that situation in first order logic, and the fact that you can't have it is an immediate consequence of the fact that it's sound and complete, and that means basically that you cannot express the idea of there are only finitely many in first order terms, and so that although it's kind of nice to have a logic that's sound and complete, the price you have to pay for it is actually restricting how much can be expressed in the language, because if you allow too much to be expressed, then it won't be possible for it to be sound and complete. And so although it's, I mean, this is a good example, of course, of somebody who's a first orderist is Quine, who absolutely loathes higher order logic, and he would regard the fact that first order logic is sound and complete as a huge advantage, but it's actually just a manifestation of the expressive weakness of first order logics.
I think we are out of time, but there is one question.
Yeah, there is one question from
Yes, am I audible?
Yes, you are.
Okay, thank you. I hope that it's not been ruled out that the H predicate having a property relation can be replaced with belonging to. Just to follow from your comment on quine, if you use belonging to a set and as a substitute for to use the Quinean conception of property as set conception, does the same problem arise?
Yes, I mean, I mean, you're right that is a member of is kind of the analog in set theory of has, being a member of a set, and so what happens is if you you do get the same paradox. It is exactly Russell's paradox that because instead of talking about the property of not having itself, you're talking about the set of all sets that are not members of themselves, and you get exactly the same contradiction, and then the contradiction has to be blocked in set theory by all kinds of restrictions on when you can actually form a set, so that not all predicates give you a set in set theory, and that was what I was mentioning, that there, although there are ways of handling the paradox in set theory, I mean they are very restrictive, but also they're much more plausible for sets, where you think of sets as being built out of their members, than they are for properties. But because in set theory, in set theory you don't have the principle that if there's a set and then it has a complement which has as members all and only the things that are not members of the first set. Whereas with properties, we surely want that for every property there is a property of not having the first property. And so that the two cases that then, well, they're formally analogous, but kind of once you start thinking about the metaphysics, particularly of the metaphysics of sets, it doesn't seem that the analogy goes very, very far.
Thank you very much.
Thank you for joining us today, and thank you especially to Professor Williamson for this thought-provoking talk. And just a brief reminder, next Thursday there will be the next Lugano Philosophy Colloquium, so you're invited to it. It will be on temporal logic as metaphysics, and it will be held by Professor Williamson. And I think remember to follow our social media to stay updated for future events. Thank you.